Let's see the thermal stresses problems. First problem is the rails of a railroad track are welded together at their ends when the temperature is 20 degrees Celsius. What compressive stresses is produced in the rails when the temperature is increased to 45 degrees Celsius? The coefficient of thermal expansion is 11 e to the power minus 6 per degree Celsius, and the modulus of elasticity E equal to the 210 gigapascal. So this problem is given by JNTUH Hyderabad in February 2024. Let's see the solution. So first I have to write down the given data. So here it is mentioned that rails of road track are welded together at their ends, which means since the rails are welded together, they cannot expand freely when the temperature increases. Hence, here thermal strain is prevented and compressive stresses are developed in the rails. So here given the initial temperature is the 20 degrees Celsius. Let's consider T1 equal to the 20 degrees Celsius. And what compressive stresses is produced in the rails when the temperature is increased to 45 degrees Celsius. So let's consider final temperature T2 equal to the 45 degrees Celsius. Then temperature rise, that is delta T equal to the T2 minus T1, which is equal to the 25 degrees Celsius. So and also given the coefficient of thermal expansion is 11 into 10 to the power minus 6 per degree Celsius, and also given the modulus of elasticity E equal to the 210 gigapascal, which is equal to the 210 into 10 to the power 9 Newton per meter square. So have to determine the compressive stresses. So we know the equation thermal stresses sigma equal to the E alpha delta T. So here in the data it is given the E, which is equal to the 210 into 10 to the power 9, and alpha value also given 11 into 10 to the power minus 6 per degree Celsius, and delta T temperature rise is given the 25 degrees Celsius. Then substitute all the values in the thermal stress equation. Then we will get the thermal stress. So nature is the compressive stress, that is sigma equal to the 57,750 into 10 to the power 3. So which is we can be written as, so compressive stress sigma equal to the 57.75 megapascal. Let's see the another problem. A steel bar is placed between two copper bars of the same area and length at a temperature of 15 degrees Celsius. At this stage, they are rigidly connected together at both ends. When the temperature is raised to 315 degrees Celsius, the length of the bars increased by 1.6 mm. Find the original length and stresses in bars. Take Young's modulus of the steel ES equal to the 200 gigapascal and EC Young's modulus of the copper equal to the 100 gigapascal, and alpha S coefficient of thermal expansion of the steel equal to the 0.000012 per degree Celsius, and alpha C coefficient of thermal expansion of the copper, which is equal to the 0.000018 per degree Celsius. And this problem is given by JNTUH Hyderabad in November 2017. So let's see the solution. So first I have to write down the given data. Steel bar is placed between two copper bars of the same area and length at a temperature of 15 degrees Celsius. So here given the initial temperature, let's consider T1 equal to the 15 degrees Celsius, and this is the schematic representation of the steel bar is placed between the two copper bars which having the same area and the same length. And also data, it is given the temperature is raised to 315 degrees Celsius. So which mean, so final temperature T2 equal to the 315 degrees Celsius and temperature rise delta T equal to the 300 degrees Celsius. So and also given the length of the bars increased by 1.6 mm. So increase in total length of the composite bar, which is equal to the delta, which is equal to 1.6 mm. So then you have to find the original length and stresses in the bars, and you have to consider the ES, EC, alpha S and alpha C is given. So okay, so let's see the solution. So let's consider bars are free, then so copper bar has to be freely expand. Let's consider that expansion is the delta CT. So here delta CT is the free thermal expansion in copper bar, and similarly steel bar also freely expand due to the temperature rise. Let's consider delta ST is the free thermal expansion in steel bar. So here observe that thermal expansion of the copper is greater than the thermal expansion of the steel, because coefficient of thermal expansion of the copper is greater than the coefficient of thermal expansion of the steel. So but here, so these bars are connected together, so it is like a composite bar. So expansion of both the copper and steel materials are equal. So that is the final expansion delta. So here final expansion delta equal to the expansion of the copper bar equal to the expansion of the steel bar, because these steel bar and copper bar are connected together. So these are act as a composite bar. So expansion of both the materials are equal, and that is the final expansion is delta. So in this regard, copper bar contraction takes place to come to the equal expansion. So in the copper bar, it is generate the compressive stresses. Similarly, steel bar try to expansion. So expansion takes place to come to the equal expansion. So in the steel bar, it will be generate the tensile stresses. So then amount of contraction in copper bar due to the compressive stresses, let's consider delta C sigma. Similarly, let's consider amount of expansion in the steel bar, which is equal to the delta S sigma. So which mean, so expansion of the steel bar due to the tensile stresses. So here let remember the notations. So notations are very important to solve this problem. So delta C T is the thermal expansion of the copper, and delta C sigma is the contraction of the copper bar due to the compressive stresses. Similarly, delta ST, which is the thermal expansion of the steel, and delta S sigma is the expansion of the steel bar due to the tensile stresses. Let's solve this problem. So consider this model also similar to the composite bar problems. So here I have to observe from the statics here, tensile force in steel bar equal to the compressive force in copper bar. Let's consider PS is the tensile force in steel and PC is the compressive force in copper. Then PS equal to the PC equal to the, let's consider the P. So this is the consider equation number 1. And similarly from the compactability equation, final extension of the steel equal to the final extension of the copper. So that is the delta C equal to the delta S equal to the delta. Let's consider this is the equation number 2. And we have to observe from the geometry. So here delta S equal to the delta ST plus delta S sigma, which means delta S. So final expansion of the steel equal to the thermal expansion of the steel, that is the delta ST plus expansion of the steel bar due to the tensile stresses. Similarly, we can be written as delta C. So final expansion of the copper equal to the delta CT. So expansion of the copper due to the temperature rise minus delta C sigma, which means contraction due to the compressive stresses in copper bar. So let's consider these are the equation number 3. So we know that one the delta C equal to the delta S. So from the equation 3, delta C equal to the delta CT minus delta C sigma, and delta S equal to the delta ST plus delta S sigma. So from this one we can be written as delta S sigma plus delta C sigma equal to the delta CT minus delta ST. Let's consider this is the equation number 4. So we got the 4 equations. So first I have to go for the first equation, that is the PS equal to the PC equal to the P, which means total tensile force in steel equal to the total compressive force in 2 copper bars. So we know that one the forces we can be written in the terms of the stresses, mean stress into cross sectional area. Then tensile force in steel equal to the sigma S into AS. So tensile stresses in steel bar into cross sectional area of the steel equal to the 2 times. So here 2 copper bars are there, then that's why I have to consider the 2 times 2 into sigma C AC. So cross sectional area is the double, so that's why I have to consider the 2 AC. So 2 into sigma C AC. So sigma S AS equal to the 2 sigma C AC. So from this one, here cross sectional area of the copper and steel is the same, then so AC and AS will get the cancel. We get the another equation. So sigma S equal to the 2 times of sigma C. So we have to observe the equation number 4. Delta S sigma plus delta C sigma equal to the delta CT minus delta ST. So from this one we can be written as delta S sigma, which is the expansion of the steel bar due to the tensile stresses, that is deformation of the steel bar due to the tensile forces, which means we know delta equal to PL by AE. Similarly here, delta S sigma we can be written as PSL divided by AS ES, and similarly delta C sigma we can be written as PCL divided by AC EC, which is equal to the delta C T, which means free expansion of the copper due to the temperature rise. We know the equation. So free expansion. So L alpha delta T. Similarly here delta CT, which is equal to the L alpha C delta T minus, we know that one the delta S T, which is equal to the L alpha S delta T. So this equation we can be written as PS by AS, so which is equal to the sigma S. Similarly PC by AC, which is equal to the sigma c. So then this equation we can be written as sigma s L divided by Es plus sigma c L divided by Ec equal to the L alpha c delta t minus L alpha s delta t. Here L is have to take in the common, then have to cancel. Then this equation will become the sigma s by Es plus sigma c by Ec equal to the alpha c delta t minus alpha s delta t. So we know the Es and Ec values and also alpha c and alpha s values also given in the data. Then substitute all these values. Then this equation will become the sigma s divided by 200 into 10 to the power 9 plus sigma c divided by 100 into 10 to the power 9 equal to the 0.0018. So here take the LCM, 200 into 10 to the power 9 is the LCM. Then sigma s plus 2 sigma c equal to the 200 into 10 to the power 9 into 0.0018, which is equal to the, so here we know the relation and sigma c and sigma s relation, sigma s equal to the 2 sigma c, then substitute here. Then 2 sigma c plus 2 sigma c equal to the 0.36 into 10 to the power 9. So from this one, 4 sigma c equal to the 360 into 10 to the power 6 Newton per mm square. So which is equal to the sigma c equal to the 90 MPa. So we got the stresses in the copper bar, that is the 90 MPa. So sigma c equal to the 90 megapascal. So then sigma s equal to the 2 times of sigma c, which is equal to the 180 megapascal. So we got the stresses in steel and copper bar, that is the delta s equal to the 180 Newton per mm square and sigma c equal to the 90 Newton per mm square. So next we find the length of the copper or length of the steel bar, that is capital L. So for this one I have to use the equation number 2, that is the delta equal to the delta c equal to delta s. So here it is given the final expansion delta value is given. So delta equal to the delta s or delta c. So here I am using the delta equal to the delta s. We know delta s equal to the delta st plus delta s sigma, which mean so thermal expansion in the steel bar plus expansion due to the compressive stresses in steel bar. So here delta value is the 1.6 and delta st, so which means thermal expansion in the steel bar, which is equal to the L alpha s delta t, and delta s sigma, which means expansion due to the tensile stresses in the steel bar, which is equal to the sigma s L divided by Es. So equation we can be rewrite as 1.6 equal to the L alpha s delta t plus sigma s L divided by Es. So here in the data it is given the alpha s value and delta t and Es values and sigma s value we find that 180. So substitute all these values, then equation will become the 1.6 equal to the 0.000012 into 300 into L plus 180 L divided by 200 into 10 to the power 3. So here, so Es is given in gigapascal. So we need the Newton per mm square. So I have to write down in the MPa. So in this regard, Es value is the 200 into 10 cube MPa or Newton per mm square. So then this equation will become the 1.6 equal to the 0.0036 into L plus 180 L divided by 200 into 10 cube. So here 200 into 10 cube is the LCM. So then equation will become the 1.6 into 200 into 10 cube equal to the 0.0036 into 200 into 10 cube into L plus 180 L. Then this equation will become the 320,000 equal to the 720 L plus 180 L. Then which is equal to the 320,000 equal to the 900 L and L equal to the 355.56 mm. So this is the solution, and length of the bar is the 355.56 mm, and stresses in steel bar is the 180 Newton per mm square, and stresses in copper bar is the 90 Newton per mm square. And thank you.